In this section, we want to talk about entropy from a slightly different perspective. And this perspective involves the second and third law of thermodynamics. So the second law of thermodynamics we already talked about in the previous section. And one of the ways we thought about it is a spontaneous process will always have an increase of entropy of the universe. So if the delta S of the universe is greater than 0, the process is spontaneous. If it's less than 0, it's non-spontaneous, but spontaneous in the opposite direction. And if it's equal to 0, it's reversible, or the system is at equilibrium. The third law of thermodynamics tells us that the entropy of a pure, perfectly crystalline substance at 0 K, or absolute 0, is 0. So what you're going to find is that entropies are something you can look up on a table, just like enthalpies were something you could look up on a table in previous chapter in this book. And when you look these up on a table, when you look up the enthalpy, you find that for elements, the enthalpy of formation is 0. But when you look up the entropy, it is not. And the reason for that is that in the standard state, at 25 degrees C, it's not a perfectly crystalline substance at 0 K. So therefore, it's not going to be 0. Before we talk about the mathematical equation, which is going to look very similar to a mathematical equation you've seen before, I want to remind us about what a state function is, because entropy, like enthalpy, and even like Gibbs free energy, which we'll talk about in a little while, is a state function. Altitude is also a state function. So if a hiker starts at this point of the mountain and finishes at this point of the mountain, their change in altitude is the same whether they follow this red path or they follow this blue path. And truthfully, if they got in a helicopter right here and then flew to the top of the mountain, their change in altitude would be the same. So a state function is a function where the path doesn't matter. So the change in altitude here, and altitude is a state function, is independent of how the person got from here to here. So let's put this into considerations of entropy and repeat or refresh what we just talked about. Entropy, like enthalpy, is a state function and is independent of the path. Entropy can be looked up from tables like enthalpy, and we can calculate it using this reaction, which is the summation of the products minus the reactants. One difference between enthalpy and entropy is that the entropy of elements is not 0. So if we look at hydrogen gas here, its entropy at 298 or 25 degrees C is 130.57. If we were to look up the enthalpy of hydrogen gas, H2, it would be 0, the enthalpy of formation, by definition. So the reason that this works, this products minus reactants, the same as for delta H, is because these are a state function. So essentially what we're doing is we're taking the reactants and we're destroying them, and then we're taking those elements and combining them back together and forming the products. So if we look at the difference between the products, which are positive, minus the reactants, which are negative, because it's minus the reactants, we can find the overall entropy of the reaction, so delta S naught. This is exactly the same as delta H that you've done in the past, quite a long time ago probably, but it was a topic in General Chemistry 1. So let's look at an actual example here where we can calculate delta S in this way. And as I showed on the previous slide, there's a table of these S's, but that being said, if it was like an exam or something like that, you would be given these. You wouldn't have to memorize them, but that table came right out of the OpenStax book. So it says, what is the delta S of the reaction for the following reaction? And we have hydrogen plus oxygen yields 2 water. And then it says, before doing the math, should the delta S of the reaction be positive or negative? Okay, so the delta S of the reaction in terms of positive or negative, we can do this like we did in the previous section. So here we have 3 moles of gas, and over here we have 2 moles of gas. So we had 3 moles, now we have 2 moles, we lost a mole of gas. So we can say that delta S is going to be negative. Now, before I actually solve this problem, I just want to talk for 1 second about this standard state stuff, because it will become important at the very end of this chapter. The standard states have to do with concentrations and temperatures and sometimes pressures if they're gases. So the pressure of the standard state is 1 atmosphere. The temperature is 25 degrees Celsius or 298 K. And the pressure, I think I said pressure is 1 atmosphere. The concentration would be 1 molar if it were in concentration units. So this is basically standard states. Sometimes reactions behave differently when they're not in standard states, which we'll talk about later in the chapter, but it wouldn't apply to a question like this. So these in joules per mole K are given in terms of their standard states, and you can tell because there's the naught sign here. The other thing to note here is that entropies are given in joules per mole K. Enthalpies, which we learned about delta H's before, those are given in kilojoules per mole. So always remember that, because we're going to use equations in a little while that can contain both H's and S's, that S's are in joules and H's are in kilojoules on standard tables. All right, now we can do this. The delta S naught of the reaction equals N times the products minus N times the reactants. N just means the number of moles. This is joules per 1 mole. Well, if we're going to have react 2 moles, we're going to have to double it. Or if we're going to form 2 moles, we're going to have to double it. So in this case, for water, we form 2 moles of water. So we're going to take 2 times 188.8 joules per K. Okay. I usually leave the mole out, so I don't have to put the mole on this, but if you want to, you can put this as 2 moles, and this is joules per mole K. All right, minus the first reactant, and the first reactant is hydrogen, and there's 2 of them. So 2 times 130.7 joules per K, plus the other reactant, which is oxygen, and there's only 1 of them. So then I can just add the 205.5 joules per K. And when I do all that math, I find that delta S naught for this reaction is equal to minus 89.3 joules per K. Okay, so this is for the reaction as written. Note that I predicted that this would be negative because we had 3 moles of gas forming 2 moles of gas. But here now I can actually calculate how negative it will be by using products minus reactants. This is exactly the same as it is for delta H, and you're actually going to see this equation one more time for delta G, this products minus reactants. So this can be a useful way of finding entropies, enthalpies, and Gibbs free energies. Note that it works again because all of these things are state functions and independent of the path. In the next section, we'll look at Gibbs free energy and combining these enthalpies and entropies in order to calculate that.